Hello guys, welcome back to another video of Computer Vision with PyTorch series. In today's video, we'll be creating our baseline model, which is our first model of this series. So our model will look something like this. So this is the model's architecture. But before creating our model, let us quickly recap what we did in our previous videos. So in our previous videos, we created or imported dataset from Torch Vision. The dataset we imported was Flatten dataset. So Flatten dataset contains 28 by 28 pixels grayscale images, which is 70,000 images. We also visualized images using matplotlib. And then in our previous video, we created train and test data loaders. So we created data loaders because we cannot send 60,000 image tensors while training our model because it will be memory inefficient. So to solve that problem, what we did was we created batches. So we created different batch of our training data. So in each batch, there was 32 images. So currently train data contains 60,000 images. So if we group 32 images in one batch, that will result in 1875 batches. And similarly, the batches for test dataset is 313 batches. So in today's video, what we'll be doing is we'll be creating baseline model. But before, if you haven't accessed the playlist, I highly recommend you to access the playlist and watch previous videos. So let us continue with today's videos, which is creation of baseline model. So the model we'll be creating will look something like this. Input layer will have nodes, and then we'll have one hidden layer which will have 10 nodes, and there will be output layer. So output layer will give numbers which will look something like this, and they are called logits. Now we want to convert logits to probabilities. So to convert logits to probabilities, we will pass this logits through softmax activation function. So after passing through softmax activation, it will give outputs like this, which is probabilities. So if you sum up this, it will result to 1. So currently there are 10 probabilities because in our Flatten dataset there are 10 classes. So if you look here, so the highest probability is the first one. So this might mean that the image that the model is trying to predict is t-shirt/top. So if we look at this architecture, you can see that there is flatten layer, and you might question what is the use of flatten layer. So currently our image has 3 dimensions, which is first is color channel, second is height, and third is width. But the thing is that our model cannot accept 3 dimensions. It can only accept 1 dimension. So to convert our 3-dimension image to 1 dimension, we should pass it through flatten layer, and then from flatten layer, it should go through input layer. So how flatten layer works is that it will change our 3 dimension to 1 dimension, and it will do so by multiplying this second and third dimension. So it will multiply 28 times 28, which will have 784 nodes in our input layer. So this is how our model will look like. Don't worry if you don't understand how flatten layer works. We will just see that in a minute. So let us continue with today's video. So let us create a flatten layer and let us see how flatten layer actually works. And then we'll move on to creating our baseline model. So let us create a flatten layer. But before creating flatten layer, we will create flatten layer from NN module. So NN module should be imported like this. So from Torch, we will import NN, and then nn.flatten will create a flatten layer. So let us store flatten layer in flatten layer variable. So now what we want to do is our train features batch currently contains 32 images. So let us take first image from that batch. So train features batch, and if I index to 0, that will give me the first image, and let us store in the variable x. Now what I want to do is I want to pass this image through flatten layer, which is I want to pass x through flatten layer. So that should convert 3-dimensional image to 1 dimension. So let us visualize how this happens. So I will call flatten layer and I will pass x. So let us store that in variable x flattened. And let us also print the shapes so that we can visualize how flatten layer is actually working. So print format string shape of x before, which should be x dot shape, and let us also print shape after passing through flatten layer. So shape of x after, and x flattened dot shape. So let us print this and let us see how flatten layer is working. So you can see that the shape of x before was 3-dimensional, and after passing through flatten layer, the shape was 1 dimension, which is 784. And then we can pass these 784 nodes to our input layer. So this is how flatten layer works. I hope you're clear. So let us, before creating our model, let us set device agnostic code. So device agnostic code is something that will automatically detect which device you're working on, and then it will make everything structured. So later on we'll not get errors like device mismatch. So let us store the current device in device variable, and we want our device to be CUDA if torch.CUDA is available, else we want our device to be CPU. So if CUDA is available, we want our device to be CUDA, and if it's not available, then it should be CPU. So let us see what device we are currently on. We are currently on CPU. So let us create our first model. And our first model will create by using nn.module class. So if you don't understand how nn.module class is used to create a new class or new model, I highly recommend you to watch my previous videos from this series and then continue on this. So let us create our first model. So let us name our model as Fasten MNest model V0, and we will use nn.module. Also, let us create a constructor. So def init, so it should be underscore init, and then self, and we will also pass certain parameters. So input, will pass input shape, which will be type of integer, and then we'll pass hidden units, which will also be integer, and then we'll pass output shape, which will be integer again. So if you don't understand these parameters right now, don't worry, when we make the model and pass these parameters, you will understand. So let us invoke the superclass constructor init, and let us now create our layer. So I will call my layer as stack layer, and let us do nn.sequential. So we are creating a sequential layer where we'll add layers sequence by sequence. So first layer should be flatten, again flatten layer, because we need to convert our 3-dimensional images to 1 dimension, because our model can only accept 1 dimension. So we're setting our flatten layer at the beginning. Now let us create our linear layer. Linear, and the input shape or in features should be our input shape, which we will pass while creating a model. So input shape, and then out features should be hidden units. Again, don't worry, we'll understand this while we're creating our model or while we're instantiating this class. So in features should be the same as the out features of previous layer. So it should be hidden units, and out features should be output shape. So now let us create our forward method. It is mandatory to create forward method because we are using nn.module class. So def forward, first parameter should be self, and then I'll pass my data through forward method, and then what I'll do is I'll return the output after passing through stack layer. So let us run this cell. Now let us create our model. So I'd like to call my model as model 0, and let us create object of this class. So I need to pass certain parameters. So first parameter is input shape. So what should the input shape be? So if you remember, nn.flatten will multiply my second and third dimension, which is it will multiply 28 times 28, which will be 784. So what I need to do is this layer should accept the output from this layer, and this layer will give 784. So what I need to do is I need to multiply 28 times 28. I hope you understood that. Now let us pass our hidden units. So hidden units, we want 10 because in our hidden layer, we want 10 nodes. So let us pass hidden units as 10. And let us also put output shape. The output shape should be the length of our class names, which should be 10 because the fashion MNIST dataset contains 10 different classes. And we also want our device to be on the target device, which is CPU for now. So let us run this cell and we've created our model. Our model is in target device. So what we need to do is we also need to send the model parameters to the target device. So let us send the model parameter to the target device. So model 0 dot parameters dot device. So this will send my model parameters to the target device, which is CPU. So let us see how this model actually works. But let us also visualize our model. So our model currently has 3 layers, which is flatten layer, linear layer, and another linear layer, which is the output. So our output will have 10 different numbers. So our numbers will initially be logits, which are just numerically unstable. So we need to pass it through softmax activation, and then it will convert to probabilities. So let us test how our model performs with a dummy data. So let us create a dummy data. Let us name this as xDummy. And let us create a random image tensor. So torch.rand. We want 4 dimension. So 1, 1, 28, 28. The first dimension will be batch size. Second dimension will be color channel. Third dimension will be height. And fourth dimension will be the width. So let us store the model output in wipe_red. So through our model 0, we need to pass xDummy. So since our model is on target device, our model parameters is on target device, we also need to send the data that we pass through our model to the target device. So let us put to device. Okay. So let us see how wipe_red looks like. Okay, so we're getting an error. The error we're getting is because of the typo. Instead of comma, we added full stop. So let us run this cell again. And you can see that the model outputs something like this. So we know that these are just numbers, which is something like this. So it's currently just unstable numbers. So now let us find the maximum number. So to find the index of maximum number, what we need to do is let us do wipe_red.argmax and let us pass dimension equals to 1 and let us store that in the variable wipe_red. So what this line will do is that it will find the maximum number and it will return the index which has the maximum number. So in this case, looks like the maximum number is first one. So it will return 0. So wipe_red will have 0 and we need to index through class names and then let us pass the index. This should return the cloth that it actually is. So our model predicts that this image tensor is short. So currently our model is just doing some random guess because initially the model parameters are very, very random. And when the model parameters are random, it will give just random output. But you see the working. We pass data through our model. It will give some random number. We'll find the maximum argument and then we'll pass maximum argument to index through class names and it will return which image it actually belongs to. So this is how our model will work. So let us train our model. But before training our model, what we need to do is we need to set our loss function and optimizer. So let us set our loss function. So let us add a comment setting loss function and optimizer. So let us set our loss function nn.cross entropy loss. So let us briefly talk about cross entropy loss. Cross entropy loss is used for multi-class classification problem. So cross entropy loss has internal application of softmax activation. So we know we don't need to manually use softmax activation in our model. As we can see that our model has not implemented softmax activation. That is because softmax activation will automatically used by cross entropy loss. So what this will do is that our model will predict these numbers, and cross entropy function will automatically apply softmax activation and then convert into probabilities, and then it will identify how bad or how good our model predicted. So this was our loss function. Let us also select our optimizer. So we want our optimizer to be stochastic gradient descent, so SGD, and we have to pass model parameters to this, and our model parameters is model 0 dot parameters, and the learning rate we can specify as 0.1, which seems to be good number, but then we can experiment and change this. So let us run our cell. We have set our loss function. We also have set our optimizer. Now what I want to do is I want to create a function to calculate the accuracy. So the function should calculate the accuracy and should return accuracy percentage. So let us create a function real quickly. So accuracy function, and accuracy function should accept ypred and ytrue. So ypred is the value that is predicted by model and ytrue is the actual value. So let us store the very correct number of model prediction in correct variable, and what we'll do is torch.eq. We will compare ytrue to ypred, and then let us calculate the sum and item. So this will calculate how many parameters were predicted by the model correctly. So this will compare my model's prediction to actual true label, and then it will return how many were correct. And now let us return accuracy by converting it to percentage. So let's create another variable acc, and then let us divide our correct by the length of ypred, and if we multiply that with 100, this should give me the percentage, and let us return the accuracy. So this function should give me the accuracy of my model. Let us run the cell, and now what we want to do is let us train our model. But last one thing, and I promise this is the last thing we do before training our model, let us keep track of time. So what we want to do is we also want to keep track of time, because another important metric to analyze the performance of our model is actually to keep track of time, is to actually calculate how long our model took for training. So to keep track of time, let us define a function. So def print train time. So this function will return how long my model took to train the model. So I'll pass certain parameters to my model. So first will be start, which will be the starting time. And if you don't understand, just do not worry. While we implement this function, you will understand it. So end will be the end time, which will be a float data point, and we'll also pass device. So device will be of type torch.device, and let us set to none for now. So we will calculate total time, which will be end minus start, and then we'll print with nice formatting. So train time on whatever the device we pass is total time, and we will output 3 decimal places and seconds. So now let us train our model. So now comes the real fun part, training our model. So let us train our model. Let me quickly add a text, model training. So to train our model, we want to import one thing, which is from tqdm.auto import tqdm. So tqdm is used to track the progress of our model training phase. You will understand this while we run this cell. So now what we want to do is we want to set manual seed. So manual seed is used for reproducibility, and let us do start time equals to timer. So what will this do is that it will, so what start time will do is that it will give the current time. So let us add a code cell just here and let us see how it works. So from time it, what I want to do is import default timer and alias this as timer. So if you look at this, I will show you how to use this timer. So while we do timer and print start time, okay, so it's a small timer. So you can see that it gives current time. So if I have some lines of code in between, and then I have another time which is end time, and I also return the time, and I call my function which is the custom function that I just created, print train time, and I pass my start time. So I need to pass start equals to start time, and if I pass end equals to end time, and device equals to my target device. So what this should return is something like this. So train time is 0 seconds. So this will give me current time, this will give me current time, and I want to calculate how long it took to run this code. So these are just comments, so that is why the time is 0 seconds. So this is what timer will do, and this is how print function will do, our custom print train time function will do. So let us continue training our model. So we want our model to be trained and tested on 3 epochs. And now let us loop through each epoch. So for each epoch in TQDM, so TQDM is used for progress bar, and we want to loop for each epochs. So let us define how our model should train. So let us add a print statement for visualization. So epoch, and let us in new line do something like this. Okay, so now let us create our training loop. So initially I want my train loss to be 0, and now what I want to do is I have created train data loader and test data loader. So if you look, train data loader, my train, okay, so let us visualize length of my train data loader. So the length of my train data loader is 1875, which means that I have 1875 batches, and in one batch I have 32 images. So what I want to do is I have to loop through every batches. So let us add a loop statement. So for every batch it x y, and I have a method enumerate to train data loader. So what this will do is enumerate train data loader will return me the batch, which is the current batch, and it will also return me the data in each batch. So suppose batch 1 has some features and its labels. So batch 2 will also have some data and labels. So for example, enumerate train data loader will return me the first batch in first loop, and then it will return 32 image labels and 32 image features. So let us write our training loop or training code inside this loop. So I want my data to be on the target device. So let us move our data to the target device. So x to target device and y dot to target device. So this will move my data to target device. And now let us write our training code. So first of all, what I want is I want my model to be on training mode. So model in training mode. So my model is model 0 and I want to put in training mode. So if you don't understand what training mode is, how forward pass works, how loss calculation optimizer works, then I highly recommend you to watch my previous videos. But with this line of code, what we're doing is we're putting our model to training mode. Now in second step, what we want to do is I want to perform forward propagation or forward pass. So forward pass, and through our model, I want to pass my my features, which will give me something like this, which are losits. And what I want to do is, now I want to calculate loss function. My loss function is cross entropy loss, which will automatically apply softmax activation and turn it into probabilities. So I don't need to perform any conversion manually. I can just call my loss function. So loss function or loss calculation. So my loss will be loss function, and I need to pass the losits and the actual label, which is y. So what I want to do is, for every batch I want to calculate average loss. So what I want to do is train loss initially, which is 0. I want to add the loss in train loss. So in every batch I am appending loss to the train loss. And now let us calculate, or let us reset the optimizer, because in every batch or in every epoch the optimizer or gradient will be appended. So we need to clear the gradients before performing backward pass. So optimizer 0 grad, optimizer dot 0 grad. Now let us perform backward propagation. 5 is back pass, and we will do loss dot backward. And now let us do optimizer step. Optimizer step is because we need to update weight and bias model parameters. So optimizer step, which is optimizer dot step. Now in train loss we have added all the loss for each batch. Now let us come one step outside of this loop and let us calculate the average train loss. So average train loss will be train loss divided by train loss by length of my train data loader, which is 1875 or something like that. So what this will do is, it will divide my train loss with the length of my train data loader, which is 1875, and this will give me average train loss. Average train loss. So this was my training loop, and in similar way let us write our training loop. So training loop or test loop, test loop. So let us put our model to evaluation mode. So this will turn off gradient tracking and much more. So in similar way we did here, train loss equals to 0 because we want to calculate average train loss. Here we will do test loss equals to 0, and also we will do test accuracy to 0 because we also want to calculate accuracy. Remember, we created accuracy function for calculating the accuracy percentage. Now very similar to what we did in our training loop, we will do the same for our testing loop. So x test, y test in enumerate test data loader. So our test data loader contains 313 batches, and for every batch this will return me the batch number and my features and then the labels. So for first batch it will give me 32 features and then 32 labels. So let us write our training code. So again, we need to pass or convert this data to our target device, because our model is on target device, our model parameter is on target device. We also need to pass our data through target device. So let us convert, or let us put our data to the target device. So xtest dot to device, and we also want ytest to be on target device. So now let us write our training loop or training code. So first is forward pass. Similar to training, we'll pass xtest through our model. So our model will then return losits. Let us store in the variable y losits. And now let us calculate loss. So second will be loss calculation. So we need to call our loss function, and then we need to pass losits and the actual label, which is y test. So this will give me loss or test loss, and then we want to add every test loss and store it in the test loss variable as well. So this will give me train loss for every batches. And now let us also calculate accuracy, as we have already defined accuracy function. So to calculate accuracy, let us call our accuracy function, and then let us pass ypred. So ypred is the value that has been given by our model, so that is y losits, and then we need to find the maximum number, and then we need to return the index of that maximum. So what we're doing is, from here we are identifying which has the maximum number. So for example, here we have the first number is maximum, so the output for this code would be 0, because in index 0 maximum number is present. So we're calculating accuracy function this way, and let us store accuracy in variable test accuracy. And we also need to, for every batch, we will add up the accuracy. And just one step outside of this loop, what you need to do is we need to calculate average test accuracy and test loss. So test loss divide equals to length of test data loader, very similar to what we did in our training loop. So also training test accuracy should be similar to test loss, length of test data loader. So let us add print statement to check out what's happening in each loop and in each epoch. So let us add a print statement right here, and let us see what's happening in each epoch. So we want to see test loss or train loss, and then we want to see test loss, which is in the variable test loss. And then let us also print test accuracy, test accuracy and percentage. So we need to also keep track of our time. We have defined the start time. Let us also define the end time, so timer, and let us call our print train time function. So this print train time function will return the difference between start and end time. So start time n equals to our end time, and device will be our target device. So let us run this cell. Okay, let's store this in the variable time taken. Okay, so now let us run this cell. This cell should perform the training and testing for every batches and for 3 epochs. This should also show me the progress bar and should also show how long it took for the model to train. Let us run our cell. So we can see that model training is going on. So currently it is on first epoch, which is 0. So okay, we're returning, this accuracy function is returning error, which is, okay, so our accuracy function returned error because what we did was we forgot to pass y true. So let us pass our y true because we forgot to pass our actual label, which is y test. So let us run our cell again, and first epoch is currently on training. So first epoch, see in our first epoch the train loss was 0.47, test loss was 4865 and accuracy was 82. In our second epoch, the test loss didn't decrease by much, and test loss also didn't decrease by much, but accuracy improved a little. And in our last epoch, the loss went down up to 0.44. Test loss was 0.47, which is same as the second epoch, and then test accuracy was the same as second epoch. And we can also see that the progress bar is showing nice and very good because of our TKDM. So we can see our model performance. We can see that the model took 29 seconds for training, and if we look at each loss in every epoch, we can see that the model loss is not, the train loss is not going down by much, and similarly test loss is also not going down by much, and accuracy also remains same across all epochs. So looks like our model is not learning very well on each epochs, but the accuracy is quite okay. But again, this is our baseline model. We expect our model to perform a little bad, but we know we'll create further models and improve this model. So let us create an evaluation function and evaluate our model. So we will be creating function because we need to reuse the code many times in further videos. So let us create function. So we will name the function as evaluation model or evaluate model, and the model should accept certain parameters as model. So which model it should evaluate, the data, which is test data loader. So it should be of type torch.utils.data.data loader. So model evaluation should happen on test data loader. So we also need loss function. So it will be of type torch.nn.module, and then accuracy function. Okay, so let us quickly create our evaluation model. Our evaluation model function will be similar to our testing code. So let us quickly write our evaluation. So okay, we have written our evaluate model function. So it is very similar to what we did in our test loop. We have put our model to evaluation mode. We have also, okay, here's a typo. We have defined our context manager, and then we looped through our test data loader. So it will return our batches, and it will give 32 features, 32 labels. And then we have sent our data to target device because model and parameter are on target device. So we also need to pass our data to target device. We have passed our X test to the target device. Okay, we have passed our X test to the model. Our model will give losses, and then we have calculate loss, accuracy, and then we have also calculated accuracy and loss and we also have calculated average test loss and accuracy for each batch. And then we have returned the dictionary. We have returned model name, we have returned model loss, and then model accuracy. So let us run this cell. Okay, torch.data.data. Okay, the data loader L should be capital. So we have successfully run the cell. Now let us pass our model and let us use this evaluate model. So let us call our evaluate model function, and let us pass our model. So first parameter we need to pass is our model. So our model is model 0, and then we also need to pass our test data loader, which is test data loader. So it uses test data loaders and it will evaluate the model performance. So we also need to pass loss function, which is loss function, and we also need to pass accuracy function. So let us store the result of this function in a variable as model 0 results. So okay, so another typo is that the name should be here underscore underscore. Let us run this cell again, and let us run this cell again. So this should give me my model performance. So our model is Fashion MNIST model V0. So our model loss on test dataset is 0.4718 and accuracy is 83%. So accuracy is not very bad, but the model loss is 0.47, which is 47% loss. So our model is doing good as guessing. So what we want to do is, now in our next video, what we want to do is we want to build on this model. So we will use this baseline model, and then we will further enhance our model and then try to decrease the loss and increase the model accuracy. So we want our accuracy to be as close to 100. Currently it's 83%, which means that out of 100 samples of test data, it predicted 83 images correctly. So to sum up, what we did in today's video is that we understand how flatten layer works. We passed our data through flatten layer, and then we created our model. So we understood how flatten layer works. We created our model where we had flatten layer, linear layer, two linear layers, where one was input layer and another was output layer. Our hidden layer had 10 units. We created our model, and then we passed our model to parameter device or to target device. We passed our model parameters to target device. We can see our model was such. We set up loss function and optimizer. We defined accuracy function for calculating the accuracy of our model. We also defined a function for printing the train time. So this would calculate the total time my model took to train or test. Then we trained our model. We also created our train. Then we created train and test loop, where we see that in each epoch the train loss was going down but not that much, and accuracy was also being high but not that much. And then we finally evaluated our model, and we can see the evaluation result, which is model loss is 0.47 and model accuracy is 83%. So if you learned something from this video, please do not forget to like, and please do not forget to access the playlist, which is Computer Vision series. And in our next video, what we'll be doing is we'll be improving this model and trying to reach the model accuracy as close to 100%. Thank you for watching this video, and see you in the next video.